Good morning, guys. Actually, today's topic is transmission line equations. But before going to this topic, what we learn so far from first class onwards, right? What we learn actually from transmission lines theory. Okay, what exactly mean by transmission line? Transmission line is the physical medium which is used to transfer information from one place to another place. It contains two ends. Uh, first, source end and destination end. That source end is also called as a signal generator or a signal transmission end, and destination end is called load. Okay, just like you and me. Okay, I am the source and you are the destination. In between, uh, there exists transmission line medium. Of course, some of the transmission lines are physically touchable, and some of the transmission lines are not physically touchable. Okay, okay. In general phenomena, transmission line is the physical medium. Those are suitable for only low frequencies. Okay, that is the point you learn. And types of transmission lines already you know: two wire line, coaxial, and waveguide. In that again, rectangular and circular. Okay, why I am repeatedly recap this topic before going to the actual topic is at the end of this unit. At the end of this unit, okay, definitely you okay, and if you are willing, then definitely you learn something from this unit. Okay, and without refer any topic or without refer any textbook, without refer any material, uh, okay, in general you are having some topics, you best aware of it. Okay, that is my motto. That's why I want to before going to the actual topic, I recapping from first class onwards every time. Okay, it may take just 5 minutes. Okay, and before adding our students, again, maximum number of students, just I am recapping these topics. Okay, what are the differences of transmission lines studied? Two wide line, coaxial line, waveguide in the rectangular and circular waveguides. Again, planar transmission lines, stripe line, microstrip line, slot line, and fine line. Okay, what is the purpose of these planar transmission lines? Where exactly they are suitable? Okay, the transmission lines are suitable, especially in ICs. Okay, why? Because ICs are always okay, very small in size. Okay, establishing the transmission line within the ICs is very difficult. That's why we always prefer such a type of stripe line, micro strip line, slot line, and fine line transmission lines. Okay, they are called planar transmission lines, and okay, they are not having any bends, okay, or zigzag in nature. Okay, and analysis of difference between the low frequency and high frequencies. Already I told you low frequency and high frequencies difference. Okay, high frequency meant by radiation effect, right? High frequencies means by radiation effect. Okay, actually the radiation is the time derived from radiate. Okay, liable to radiate. Okay, but high frequencies are unable to radiate, unable to transmitted through transmission lines because of that problem called skin effect. Okay, we will discuss later the problem called skin effect. Okay, in the electromagnetic fields. Okay, that's why that high frequency signals are always transmitted by means of electromagnetic waves without any medium. Okay, and low frequency transmission lines. Low frequency means, and if we want to radiate high frequencies, if we want to propagate high frequencies through transmission lines, but the transmission lines must having insulations, right? Thick insulations like coaxial cable. Okay, inner insulator and outer insulator, inner conductor and outer conductor. Okay, such a type of structure is required. Okay, our transmission line is able to, I mean, that coaxial cable transmission line is able to radiate the frequencies around 30 megahertz. Okay, remember that point. Okay, that is the key difference between the low frequencies and high frequencies, and here gives the relation between lambda c and f. Lambda equal to c by f is the fundamental relation between wavelength and frequency. Okay, and next we discussed metallic cable transmission line medium. Metallic cable, okay, the name itself indicates it is the metallic, okay, with some insulation coating on surface. Okay, metallic cable transmission lines, which is made up with metallic transmission metal. Okay, metal is the material. Okay, in that there are two types of transmission lines are registered as balanced and unbalanced transmission lines. Metallic transmission lines equivalent circuit contains or LGC as the primary components. They are primary constants, and beta and Z naught or gamma and Z naught. Sorry, propagation constant and characteristic impedance. Gamma and Z naught are the secondary constants. That is the term you learned. A wave propagation on the metallic transmission line. How that wave is propagated in metallic transmission lines. The wave propagated in transmission line is always in the form of TEM. Okay, transverse electromagnetic, transverse electric magnetic, right? TEM mode, TEM. గుర్తుపెట్టుకోండి. Okay, TEM. Okay, that is also a very important competitive bit. Okay, at the same time, transmission line losses. What are the different types of losses are existed during the propagation of electromagnetic waves in the transmission line? Okay, that is that those are the okay, and I mean copper losses, iron losses, eddy current losses. Okay, okay, some of the transmission line losses are there. We discussed later. Okay, phasor current and voltages. Okay, phasor form of the voltages and currents. Okay, phasor form. Okay, single section of transmission line. Already I know. Okay, already I told you. Okay, single section of transmission line or segmented transmission line. Characteristic impedance and propagation constants are the secondary constants of the transmission line, and standing waves and reflection coefficient. Okay, these are the very crucial, and we are always dealing with these two only. Okay, in this entire transmission line, standing waves and reflection coefficient. Okay. See here, types of transmission lines are also discussed: coaxial, twisted pair, open wire, twin laid. See here, metallic transmission lines is an open wire, just like a railway track. Okay, they are always separated with some insulator with a uniform distance among. Okay, among them, right? And between the rails. Okay, and this is the twin lead. Okay, twin lead transmission lines contains two leads. These two leads are connected. Correct connection port. Those are having some connection port, and internally it's having a some flexible metallic and just like a wire. Okay, flexible wire, flexible conducting wire, twin lead. This is the twisted pair. See here, two wires are twisted like this. Okay, this is called twisted pair transmission line, and this is the coaxial cable already, actually these are the coaxial components, and how the two coaxial cables are connected to each other is the purpose of the connectors, and coaxial terminating sections are also there. Okay, these are the coaxial sections. And what is meant by attenuator? Attenuator is nothing but a resistor network. There are basically two types of the attenuators are there: fixed attenuator and variable attenuator. Okay, yeah. Okay, along with these two, they also mention the step attenuator, and just like our fan regulator. Okay, fan regulator is always the step attenuator. Okay, but in the fan regulator, that is connected in reverse. Okay, when steps increases, okay, regulator increases step one, step two, step three, step four. Okay, and when the increases, resistance value decreases, and when step value increases, resistance value decreases. Okay, when the resistance value decreases, current flowing through the wire increases, right? And whenever the current flowing through the wire increases, fan speed increases, right? Okay, and when increases from step one to step two, fan speed increases, right? Step two to step three, step three to step four. Okay, when I increases the steps, okay, step value, fan speed also increases. How it is possible? Okay, it is possible by the means of decreasing the resistance for each step, right? And whenever a parallel value increases, and actually internally there that is connected in parallel, okay, not series, that is a parallel connection. And whenever that parallel value increases, resistance value decreases. Okay, how would you know already? Okay, and when two 10 ohms resistors are connected in series, what is the total resistance? 20 ohms. Okay, for suppose that two 10 ohms resistors are connected in parallel, what is the net resistance? 5 ohms, right? And whenever the parallel connection increases, net resistance value decreases. Okay. Uh, Here the attenuators are used to reduce the signal strength. Okay, attenuator is always the resistor network. Here they are considered as the two types: fixed attenuators and variable attenuators. Variable attenuators is again step attenuator is the one type. Okay, just like a fan regulator. Okay, coaxial components. There is no need of this. Okay, already you discussed in the yesterday's class. Okay, all these topics, metallic transmission lines. Okay, let's go through these images. Already I shared this PPT in our WhatsApp group. See here, ideal transmission line. Ideal transmission line means the transmission line is ideal, means there is no loss. Okay. Okay, and if the transmission line is ideal, for suppose just consider our power lines. Okay, just consider our power lines. For suppose our power lines are ideal. For suppose at the one end I'm supplying 230 volts AC 50 Hz frequency. Of course, the frequency component is not changed, but when I'm applying the 230 volts at one end, at the second end, it is definitely less than 230 volts. But the transmission line is said to be ideal. When I'm supply 230 volts at one end, other end is also definitely we get 230 volts when the transmission line is ideal. But in practical case, okay, no ideal transmission lines are existed. Okay, okay, that's why ideal transmission lines are never existed. See here, conductors have a zero resistance, right? Dielectric has a zero conductance. Actually, dielectric doesn't conduct, but okay, dielectric doesn't conduct, but dielectric. It is the nature is dielectric. That's why it's also having some conducting. But ideally, conductance value is zero. Okay, possibly only with superconductors approximated by the short line. Okay, they refer like this. No capacitance or inductance. Okay, actually, when I'm switch on, actually when we consider the transmission line of length 1 kilometer, uh, when I'm switch on the light of the transmission line, okay, at one end, after that 1 kilometer, is it the light glow immediately? No, okay, definitely takes some time. Why? Because uh, after a switch on that, after when I'm switch on, okay, the electric signal propagation takes a few microseconds to milliseconds time, okay, to propagate it from one end to another end. Okay, that 1 microseconds time or 1 milliseconds time, uh, where that energy exactly lies within the wire only. Okay, and that wire process is some inductance and conductance. Okay, some capacitance and inductance, right? Okay, ideal transmission line doesn't possess that storage capability. Here, capacitance or inductance by means of storage capability of the transmission line. Okay, but ideal transmission line doesn't possess that inductance or capacitance. Okay, that's why those are the characteristics of the ideal transmission line. Okay, possibly with real line only at a DC. Already I told you what is meant by real line only at a DC. Okay, capacitance or inductance is always represented with R plus JXC and R plus JXL, right? And R minus JXC and I mean R plus 1 by JXC and R plus JXL. Okay, but when we consider ideal transmission line, means there is no losses, means there is no reactances, means there is no imaginary term. It contains only real term. Okay, that's why they mentioned as a real line only at DC. See here, this is the equivalent circuit of the transmission line. Already I told you. Okay, what are the components it's having? What are the different components? Okay, R, L, G, C, resistance, capacitance, inductance, and conductance are the primary constituents of the transmission line. That's why that's the equivalent circuit contains R, L, G, C terms. Okay, similarly, secondary constants, beta and Z naught. Beta and, sorry, gamma and Z naught. Gamma is the propagation constant and Z naught is the characteristic impedance. But of course, here not mentioned, but remember that point also. Okay, this is the two-wire parallel transmission line, electrical equivalent form. Okay, see here, or a traveling wave. Already I told you in the last class, traveling wave. Okay, and at the end, or at the one end, I am supplying the voltage V of t. Okay, which is having a magnitude of Vc, and basically it is a cosine wave. Okay, and for sine wave or cosine wave, whatever it may be. Okay, cos or cosine, whatever it may be. But generally they prefer cos omega t here. Okay, and for convenience only, and you may consider the sine wave also, there is no problem. Okay, where Vc is the magnitude, cos is the sinusoidal signal in nature. Okay, where omega is the angular frequency. See here, traveling wave. Okay, the input voltage is considered as a V of t equal to Vc cos omega t. Okay, don't confuse otherwise. Okay, it is very simple. The traveling wave can be considered as a V of z comma t equal to Vc cos omega t minus beta z, where beta is the propagation constant and z is the direction of radiation. Okay, similarly, current I of z comma t equal to Ic cos of omega t minus beta z. Okay, currents and voltages are in phase. Okay, see here Vc and Ic. Okay, currents magnitudes and voltage magnitude and current magnitude omega t minus beta z, okay, is the same angular frequency with same propagation constant and with same direction, where z is the direction of radiation. See here phase velocity. Already in the last class we defined two terms called phase velocity and group velocity. What is meant by phase velocity and what is meant by group velocity? Phase velocity is already defined. Phase velocity v sub x p, velocity equal distance by time. What is meant by distance? Distance is nothing but wavelength and how much okay, how much wave is traveled to get a phase shift of 2 5. Okay, and a complete reach this phase shift రావడానికి ఎంత distance travel చేస్తుంది, that is called its wavelength. It is always represented with lambda, right? So velocity equal to distance by time equal to velocity v equal to distance lambda by time. Time is nothing but 1 by frequency, already you know. Okay, from that we defined f lambda phase velocity vp equal to v sub x p equal to f lambda. Okay, that may be also represented as a omega by beta from the above relation. Already I told you beta lambda equal to 2 pi, how it is possible. Okay, for a one wavelength. Okay, that beta is also called as a wave number. Okay, one lambda means one is the how many waves are there at a t equal to 0, how many waves are there to represent that lambda value? One wavelength, okay, one lambda, that one is represented as a wave number. Okay, that's why that one is represented with a wave number beta lambda. Okay, equal to 2 5. From that beta equal to 5 by lambda. Okay, what is meant by omega? Omega is nothing but a frequency, but measured in radians per second. That is actually represented as a 2 5. Okay, so by substituting the above values in phase velocity, we get omega by beta is the phase velocity representation. Similarly, group velocity is nothing but a group of waves. Okay, not in practical there is no single wave present. No single wave is present. Okay, the group of waves. Okay, group of waves presented here. That's why that is represented as, of course, omega by beta, but as a when we consider as a group of waves, that's why it is considered as a differential mode, as a d omega by d beta. Okay, d omega by d beta. Okay, hence the name group velocity. Okay, wave velocity or phase velocity for a single is the omega by beta. When we consider the group of phases, okay, then it is said to be group velocity. Okay, is represented as Vz equal to d omega by d beta. Okay, that is the notation for d omega by d beta is the Vz. V suffix z is nothing but group velocity. Okay, see here, when we consider the attenuation here, we have z comma t. Already I told you, okay, how attenuation factor is included here. V of z comma t equal to Vc into cos of omega t minus beta z. Here, e power minus alpha z is the exponential term. Exponential, is it increasing or decreasing? E power minus alpha z is the exponential decay function. Means, okay, whenever the length of the wire increases, resistance value also increases, right? Resistance value increases, signal strength decreases. That signal strength decreases, is it abruptly or slowly, gradually? Okay, the signal strength decreases gradually. Okay, that's why that gradually is the representation of the exponential decay. That's why here represented as e power minus alpha z. Here minus alpha z minus indicates, here negative sign indicates exponential decay function. Okay, in the direction of z. Okay, alpha is called attenuation coefficient. It is measured in Nepers per meter. Nepers per meter. Okay, what is the attenuation in decibels per meter? Okay, here they raise the question in terms of decibels. Okay, and 8.686 dB notation. Okay, conversion. Okay, 0.115 Nepers equal to 8.686 decibels. Okay, get it? V of z comma t equal to Vc into e power minus alpha z cos of omega t minus beta z. Alpha is the attenuation coefficient, Neffers per meter. What is the attenuation in decibels per meter? Okay, that is equal to 8.686. Okay, 8.686 dB. Phasor currents and voltages. Already I told you phasor currents and voltages. And what are the possibilities of representing trigonometric form and exponential form? Okay, here when we consider the phase constant and group constant, the wave propagation along the transmission line, we must consider the electromagnetic waves in the form of exponential instead of trigonometric form. Why? Because the mathematical simplification is somewhat easy, okay, in the exponential representation, and numerical analysis is very comfort, okay, to us. That's why they always considered instead of trigonometric form, they always treated with the exponential form. See here, v of t equal to v into e power minus alpha z cos of omega t minus beta z is the and when we consider the wave with attenuation alpha, okay, that is represented like this, okay, real form, okay, real part. Already you know cos of omega t, okay, when we consider the cos x, okay, v into e power minus alpha z into cos x. Okay, what is the exponential form of cos theta or cos x or cos theta? E power j theta plus e power minus j theta by 2, right? Okay. Similarly, here instead of theta, they consider omega t minus beta z, and the same the expression is represented like this, and among that only they consider real part. Okay, instead of imaginary part, they consider only real part. That's why real part equal to v into e power minus alpha z, v into e power minus alpha z into e power minus j beta z, right? Okay, and that cos of omega t minus beta z. Okay, is it my voice is not audible properly? Okay, just a second. Okay, is it now audible? Okay, see here. Okay, that exponential form, and consider cos theta. Okay, here omega t minus beta z equal to, just assume that is the theta cos theta exponential form. Okay, e power j theta minus e power minus j theta by 2. Okay, in that they consider only the real part. Okay, see here, e power v into e power minus alpha z into e power minus j beta z into e power j omega t. Okay, and that is the Phasor form. Okay, that is the Phasor notation of that expression v into e power minus alpha z cos omega t minus beta z. See here, and that expression is considered the Phasor for the driving voltage v naught, the Phasor of the voltage at a distance x from the driving point. Okay, here they consider, and a driving point means at the source end. At the source end, okay, vx equal to v naught into e power minus alpha x into e power minus j beta x. Okay, equal to v naught into e power, and when we take the minus common here, minus alpha plus j beta into x. Okay, see here, e power minus alpha plus j beta is represented as a gamma. Alpha plus j beta is represented as a gamma. Okay, what exactly mean by gamma here? Okay, here the mention where gamma is called a propagation constant. Okay, and that propagation constant having alpha plus j beta, where alpha is called attenuation constant, where alpha is called attenuation constant, it is always measured in decibels, and beta is called phase constant or wave number. Okay, beta equal to 2 pi by lambda, already you know. Okay. Okay, from the driving point they considered at a distance of x. Okay, at a distance of x the potential is vx, right? That vx equal to v naught into e power minus alpha x into e power minus j beta x. That v naught into e power minus of alpha plus j beta into x, where e minus of alpha plus j beta, okay, is represented as gamma. Okay, that's why v naught into e power minus alpha x, where gamma is called a propagation constant. uh, and that the propagation constant by means of the summation of attenuation constant and phase constant is alpha plus j beta. Remember this point. Okay. Phasor currents and voltages as Vx equal to V naught in e power minus gamma z is the same at a distance of x. The current Ix is represented as I naught into e power minus gamma z. Okay, where I naught and V naught themselves as a phasor form notations. Okay, and their angles are not necessarily the same. Okay, and here mentioned like this, but the angles may or may not equal. For our convenience, they mentioned like this. See here, transmission line model. Okay, the equivalent circuit or LGC. Uh, they consider for a unit distance, but in practical they consider it one segment. Okay, already you know what is meant by one segment here. Okay, this is the one segment. This is the one segment. Okay, and the part which contains all primary constants. Okay, the part which contains all the primary constants as RLGC. See here, at low frequencies only resistance has to be considered. At higher frequencies capacitance and inductances must be included. Okay, all of these are distributed along the line, that's why they are called a primary constants. Okay, just a second. See here, single section of a transmission line, single section of a transmission line, single section. See here, this is the resistance R, this is the L, this is the L, this is the R again. Okay, this is the Z and this is the C or LGC. Okay, again this is R, this is L, and mean two lines. Okay, this is L and this is R. Okay, they are not considered parallel line. Okay, they considered parallel line. See here, here I am applying a distance of, okay, actually okay, this is the segment with a distance D. Okay, distance they considered as a Z. Okay, the length of the line is the length of the line is the length of the line is Z. Okay, and a differential length, that's why that is considered as delta Z. They considered differential length of the line. Okay, that notation is the delta. Okay, not a fixed length, it means Z. Okay, see here, here current passing through that line is Iz. Potential difference between these two lines is Vz. Okay, and this is the ending current Iz. Okay, and from this closed loop outgoing current, see here, and this is the Iz. Okay, and the same current is passing through that line. Okay, at the this is the source end. Okay, remember this point, and for suppose this is the destination end. Okay, and distance between that source and destination having some differential length, right? Differential length delta Z. Okay, differential length delta Z. Okay, and that may be the direction or this length. Okay. See here, this is the current Iz. The same Iz is passing through that resistance, inductance, and because of the shunting conductance and capacitance, shunting capacitance and conductance. Okay, some of the current is passing through this line and this part. Okay, and the remaining current is, see here. Here the current is Iz. Here the current is delta I. Here The current is IZ. Here the current is delta I. Okay. Similarly, here the voltage is VZ. Here the potential difference existed between these two lines after this constants is delta V. Okay, right? At the end, and according to the Kirchhoff current law, the net current here is IZ plus delta I. Voltage is VZ plus delta V. And just assume, okay, just assume, okay, total series resistance R into delta Z, total series inductance L into delta Z. Okay, here delta Z is the impedances offered by this line. Okay, differential impedances offered by this line over this length. Okay, so and simply I'm applying this KVL, okay, to this line. Simply I'm applying KVL. Okay, according to that KVL, what exactly meant by KVL? Okay, KVL, simply KVL states that if the applied voltage is V, okay, and the resulting drops, okay, at the, okay, components V1 and V2. Let us assume, okay, two components are there. At the component 1, drop is V1. At the component 2, drop is V2. Okay, then applied voltage equal to total drop is V1 plus V2. From that, delta V, V equal to applied voltage V in equal to V1 plus V2, right? According to the KVL. Okay, from that point, at the same time, see here V equal to, okay, supply voltage or differential voltage V equal to, see here, resistance into current. What exactly meant by this? R into IZ. R into IZ means resistance into current. Resistance into current means voltage, right? Okay, voltage, supply voltage V equal to resistance into current. Okay, V equal to IR, Ohm's law. Just that is Ohm's law. V equal to IR, delta V equal to R into IZ is the voltage over its length delta Z, right? Okay, along its length delta Z, the differential length of transmission line delta Z. Okay, that segmented resistance and current IZ. Okay, that is the one part. And second part is, okay, the voltage, okay, that appears across the inductance, okay, J omega L into IZ. Okay, that is also Ohm's law again, IZ into J omega L. Okay, over its length of delta Z. Okay, so delta V equal to R into delta of IZ minus J omega L into IZ. Okay, delta of IZ, right? Okay, that is the partial differential notation. See here in the second line. Okay, dVz by dz. Okay, and when we convert that delta Z to differential mode dz, okay, differential mode. So simply just simplify this. Okay, simplify this equation. Just simplify this equation. Okay, just to take the common of minus sign, R plus j omega L. Okay, R plus j omega L, R plus j omega L into Iz. Okay, okay, here the differential notation delta z is taken as a common from the both sides, left hand side and right hand side, that they convert partial differentiation into differential form directly. Okay, that's why that is called okay, this is called okay, d v of z by, again, delta z is represented as a simply dz. Okay, dvz by dz equal to, okay, when we take the minus sign as a common, r plus j omega L into Iz. Okay, dvz by dz. dvz by dz. Okay, how that change in length. Okay, what are the parameters they considered? Okay, what's length dvz by dz. See here. See here. Okay, potentials. And when we consider its exponential form, when we consider the exponential form of that vz, when we consider the exponential form of vz after the differentiation with respect to z, okay, what we get basically here the term alpha plus j beta. Okay, actually here the term existed from that above slide. Okay, here the point is skipped out. See here, when we consider vz equal to transmission line phasor form currents and voltages, v naught into e power minus e gamma z by, sorry, dv naught into, sorry, dvx by dvx by vx, or simply here dv naught by dz. Okay, simply differentiate this expression with respect to z. What we get? Minus gamma, right? And simply alpha plus j beta. That's why in this expression, simply dvz by dz in its exponential form is represented as gamma into vz, right? Gamma into vz. That's why here they directly considered as gamma into vz equal to minus of r plus j omega l into iz. Okay, from that. Daddy? Gamma into Vz equal to minus of r plus j omega L into Iz. Similarly, for the currents, delta I equal to minus of conductance into voltage, right? That is also Ohm's law. This is also Ohm's law. Okay. And here the voltage is represented with resistances and inductance, and current is represented with conductance and capacitance. Similarly, by simplifying this expression and when we consider its exponential form, gamma into Iz equal to minus of G plus j omega C G plus j omega c into Vz. Okay. Okay. All these okay are not necessary for you, but remember these 2 points: Vz and Iz expressions. Gamma into Vz equal to minus of r plus j omega L into Iz. Remember this point. Gamma into Iz equal to minus of G plus j omega c into Vz. Okay. From this, Vz and Iz expressions are minus r plus j omega L into Iz by gamma, minus of G plus j omega c into Vz by gamma. Okay. Remember this slide, okay, conveniently. See here, characteristic impedance. Okay, remember this slide. Okay, and these are the okay. Remember this expression. Okay, because only from this expression that the entire unit is covered. Vz and Iz relations, and a minus of r plus j omega L into Iz, G plus j omega c into Vz. Okay. Okay, this is the one part. Okay, these are called transmission line equation in terms of primary constants and secondary constants. Okay, primary constants and secondary constants. Okay, now the second part is characteristic impedance. Characteristic impedance. Okay, characteristic impedance and propagation constants are called propagation constants, and characteristic impedance are called secondary constants of the transmission line, right? See here, characteristic impedance. What is meant by impedance? What is meant by resistance? Resistance is nothing but voltage by current, right? Similarly, characteristic impedance. Okay, impedance is defined as resistance or impedance. Both are same, right? But then what is the difference between resistance and impedance? Resistance is really defined for DC. Okay, why? Because there is no AC component. That's why there is no reactance components existed there. Okay, when we consider characteristic impedance. Okay, and when we consider the transmission line, here the transmission lines are dealt with frequency components. Okay, not for DC. AC component is also there. That's why you consider with impedance. And notation is for the resistance we use the notation called R, and for the impedance we use the notation called Z. Okay, the ratio between the voltage and current on a line is simply defined as impedance. Okay, depends only one line geometry and dielectric. And here and they consider for AC, that's why it is mentioned like this. And here the characteristic impedance is not a function of its length. Okay, at anywhere it is defined. Okay, of course the units are same ohms. See here characteristic impedance. Okay, from that above expression, gamma into Vz equal to minus of R plus j omega L into Iz. Similarly, currents gamma into Iz equal to minus of G plus j omega C into Vz. Okay, what is meant by characteristic impedance from the above expression? Vz by Iz, right? From that Vz by Iz, simply define, simply take the ratio gamma into Vz by gamma into Iz. Gamma into Vz by gamma into Iz, 1 by 2. Vz by Z equal to R plus j omega L by G plus j omega C. Okay, Iz by Vz. From that, Vz by Z equal to square root of R plus j omega L by G plus j omega C. Okay, and here Vz into Vz square, Iz into Iz square, Vz square by Iz square. Okay, or Vz by Iz whole square. From that, square root of R plus j omega L by G plus j omega C. Okay, where that Vz by Iz is called a characteristic impedance, where R, L, G, C are called primary constants. Okay, and when we consider the line is said to be lossless. Okay, when the line is said to be lossless, R equal to 0, G equal to 0. When R equal to 0, G equal to 0, what we get? Square root of 0 plus j omega L by 0 plus j omega C. J omega get cancelled. From that, Z not equal to square root of L by C. Okay, that is the expression for characteristic impedance of a lossless transmission line. Okay, that is the notation here. Z not equal to Vz by Z equal to square root of L by C. Okay, that's all about today's class. Okay, what we'll learn in today's class, what are the expressions for wave equations in a transmission line, okay, in terms of primary and secondary constants. From that, how do you define the characteristic impedance? From that, what is the condition for lossless, okay, lossless condition. And when you consider the lossless condition, we get characteristic impedance for the lossless condition as a L by C. Okay, that's all about today's class. I will continue in the next class. Okay, thank you.